Yes, thank you, Stephanie. Our next speaker will be Axel from Stanford. He will talk to us about the using deep learning method to solve the crowd-EM.
Expectations. Yeah, thank you very much for having me. I'm very happy to present some of my recent work today. I feel like what I will talk about echoes a lot of things that we've been hearing about. So very happy to present today. And the title for my presentation is Combining Diffusion Models and Experimental Measurements for Protein Structure Determination. And I'd like to start by essentially framing the protein structure determination as what some people call an inverse problem, just to have a very general point here on the problem. So we have different experimental methods for accessing structural information. We've heard about cryo-electron microscopy, crystallography, or nuclear magnetic resonance. And essentially the challenge for a person designing a reconstruction method is to turn those measurements into structure, potentially motion. The reason this is challenging is because each measurement only provides partial and noisy information. So what the person designing the reconstruction methods has to face is essentially an inverse problem. So more specifically, that can refer to a maximum a posteriori problem or a posterior sampling problem. And if we look at ways those inverse problems have been tackled in the past, there is essentially two ways they have been addressed. And the first, I will describe it as the way of physics, and the second, more recent, as the way of data. In the way of physics, you just try to sample from or maximize a posterior distribution, which you can, using Bayes' rule, decompose as likelihood and a prior. Now, the idea is that you're going to explicitly define those two expressions, which has different benefits. The first one is that you'll use your knowledge about the forward model, and that's via the way you define the likelihood function. And if you're interested in posterior sampling, you can also have clear uncertainty estimates of your answer. However, you have to explicitly define the prior. So the prior you're using has to have a closed form expression. It has to be explicitly defined. So oftentimes it's going to be some sort of heuristic prior. And on the opposite side of the spectrum, you have the way of data, where the idea is essentially given a set of paired data. So I have measurements, and in this case, 3D models. I want to find a function that will map measurements to models that is going to be right on the data points that I have and hopefully generalize to new data points, which has a few benefits. First, it's possible to capture patterns or relationship from the data that we could not explicitly capture with closed form expression, and it's also fast at inference time. So if we ignore the time spent at training, at inference time, it's just a matter of evaluating a function, not solving a maximization problem. However, this obviously is limited by the fact that we need access to this paired data. So what I want to talk about today is kind of in between in those two worlds. This is also something Alicia was talking about earlier today. We still want to take this approach of maximizing or sampling from the posterior, where the likelihood comes from a physics-based model, but now we want to allow ourselves to use a prior that is fully data-driven, and we don't want to have that constraint of explicitly defining the prior, which has the advantage of combining the physics-based knowledge with the likelihood function and information captured from the data. And more importantly, we don't need to have access to this paired data. We only need to have access potentially to data points of X, not paired with the measurements. If we now look at how this prior distribution has been captured recently, we have recently witnessed significant progress in the space of de novo protein generation. This is exemplified by algorithms like RF diffusion, Chroma, ESM3. They all are trained on the data set of protein structures, and they enable unconditional generation, meaning sampling new structures that are supposed to be sampled from the same distribution. And if we look at how they actually work under the hood, it turns out that most of them, so in this case here, RF diffusion and Chroma, rely on diffusion models. This is not the case for all of them, and I will come back to that later. ESM3, for example, relies on autoregressive models. So the question I wanted to explore was, can we efficiently use those diffusion-based models for experimental structure determination? Essentially, can we frame the problem as this posterior sampling problem or map problem, but use a prior that will be in some way supported by the pre-trained diffusion model? So just with an image, I'm going to say the same thing. We have a set of measurements, and we also have a pre-trained diffusion model. We want a method that gives us an atomic structure. It is going to be consistent with our measurements and likely under the prior that is captured by the pre-trained diffusion model. Okay, so I'm going to break down the rest of the presentation in two parts. First, I'll talk about a very recent project where we've explored this direction, and we tried to leverage diffusion models for structure determination on a few specific examples. And in the second part, I'll be a bit more hypothetical, and I will be more asking questions actually, and I will wonder how we can go from this paradigm of protein structure determination towards dynamic characterization, which is something we've been talking about a lot today. So let's start with this first part, leveraging diffusion models for structural determination. And here I'm going to talk about a method that we've called ADP3D, and that stands for atomic denoising prior for 3D reconstruction. There is a few inverse problems we've been looking at. I would like to maybe give a disclaimer right away. So I will only give results with simulated data, and we are currently working on having results on experimental data. So this is all validation of the methods, and there's again three problems we've been looking at. The first one is atomic model refinements. In this case, we suppose that we have access to a cryo-EM density map and an incomplete atomic model that is given by an upstream model building method like Model Angelo in this case. And we want to use our method to automatically refine a model into the density map in a way that is realistic under the prior that some diffusion model has captured. So now I'm going to show the diffusion trajectory that our method gives. So in gray, this is the ground truth structure that we've been using to generate the density map. Again, this is a simulated density map. And then in rainbow colors, you see the optimized trajectory. We've been also looking at a much more simple problem, which we call a structure completion. This is essentially a linear inverse problem where we suppose that we know a subset of the Cartesian coordinates of the atoms in the structure, and we want to in-paint essentially the rest of the structure. So the framework of the method enables you to do that as well. And the third problem we've been looking into is a nonlinear inverse problem where we're assuming that we're given a sparse set of pairwise distances between residues, between the alpha carbons of a list of residues, and we want to reconstruct the full structure. Again, in a way that would be consistent with the pairwise distances and realistic under the prior that we have. And this is an idea, so combining using diffusion models to solve inverse problems is something that has been explored before in computational imaging. I'm just showing here the reverse stochastic differential equation that a diffusion model uses at inference time. And now the idea that was used to essentially leverage a diffusion model and use it to sample from a posterior is to slightly modify this SDE and use the posterior score function. So the score function is the object that I've put in blue here. And we're going to use instead the score of the posterior, which you can, using Bayes' rule, decompose as a sum of two terms. The first one directly comes from your pre-trained diffusion model. And the second one would be the likelihood score. And this is actually the thing that's hard to get, and this is not tractable. So all the methods that have been developed using diffusion models for solving inverse problems essentially differ in the way they approximate this term here, so the likelihood score. And they've been applied to linear problems like deblurring, in-painting, super resolution, but also nonlinear problems like phase retrieval or non-uniform deblurring. And again, there has been a lot of methods, and they essentially differ in how they make the approximation on the likelihood term. So we wanted to take inspiration from those methods and essentially apply them in protein space. If we look at how diffusion models are built in protein space, most of them essentially define the diffusion process in the space of backbone structures. However, they will differ in what that backbone structure space is. Some of them will use a space of 3D point clouds to represent those backbone structures. Most of them actually do. But some of them also use the space of dihedral angles, which is nice in a way because this gives you for free the SE3 equivariance that you're looking for. But also people have been looking at backbone frames. So each residue is symbolized as or represented as an element of SE3. So those are different ways to represent the space of backbone structures. But the common point that all those methods share is that under the hood, they will have a function that we will call the optimal denoiser that will take as input a noisy backbone structure and will output a denoised backbone structure. And this is the only object that we need to extract from the diffusion model in our method. So I will explain how that works. And this is an idea that came from the plug-and-play method, again, developed first in computational imaging. But the idea is that if you want to solve a maximum a posteriori problem, it's equivalent to this minimization problem where you have sum of two terms. We're going to call them F and G. And now the idea of plug-and-play method is to use a method called half quadratic splitting instead of solving this complex minimization problem. You're going to iterate between solving two potentially simpler minimization problems. And if we look more carefully at the second optimization problem that we want to solve, and if we remember that F here represents the negative log prior, and if we recognize here that this is the negative log likelihood for Gaussian noise, this optimization problem actually represents a denoising step for a Gaussian denoiser. So the takeaway here is that if you have an object that's a Gaussian denoiser that was trained in any way you want, but if you have this Gaussian denoiser, it can be used as a prior in a maximum a posteriori problem. And the advantage here is that this denoiser doesn't give you the prior function. You cannot evaluate the prior function, but the fact that you have this denoiser can be used as a prior implicitly. That's what we do here. So the way the method works is by going through this iterative procedure, where the first step is to denoise a structure. And here we've been testing two diffusion models, testing chroma and RF diffusion. For most of the results I will show that we were using chroma. And the second step is the data matching step, where we're basically taking a gradient towards maximizing the log likelihood of whatever information we have with respect to the structure. And we go through those iterative steps a certain number of times, and the structure we converge on is considered as the output of the method. So first, we validated the structure on this, the method on this linear problem that has no real equivalent, but was more as a way to evaluate if the method kind of works. So the problem we are looking at is structure completion. We suppose that the measurement that we have is a subset of the Cartesian coordinates of the atoms in the structure. So that would look like that. For example, if we have the gray ground truth structure, we assume that we only know the location of the alpha carbon that I've indicated with spheres. And I'm playing with the subsampling factor, essentially. So the larger this factor, the more difficult the problem is going to be. And I'm looking at the output of the method as a function of this subsampling factor. So what we can see is that we get something that, well, resembles the ground truth structure that always has realistic secondary structures, even when the subsampling factor is very large. And as expected, the RMSD with the target structure is going to increase with the subsampling factor. And we've compared this method, again, based on half quadratic splitting to another method. So this is indicated in blue with chroma star, which is a posterior sampling method. And we can see that over the range of subsampling factor we were using, we get a lower RMSD with the ground truth structure. And so an experiment that we also did is looking at what happens if you just remove the denoising step. So if you remove any prior, as expected, you get an RMSD that increases over all subsampling factors. Now, as I said earlier, another inverse problem we were looking at is model refinement. And to explain what we're doing, I will just briefly go over the forward modeling for LEM, but this has been done in previous talks, so I can be quick here. To have a very high level view on cryo-EM, essentially we have flash frozen an ensemble of particles. So we can assume that each atomic model we're imaging is a sample from the Boltzmann distribution at the temperature before the flash freezing operation. This atomic model is then transformed into a density map with an operator that we'll call gamma here. And then this density map is projected from an unknown view angle. Now, the step that brings you from images to density maps is usually called 3D reconstruction. And here we're looking at the second step where you want to go from a density map to an atomic model called model building or model fitting. And there is several approaches to handle model building, and they fall basically into two categories I've described earlier. A lot of state-of-the-art methods even today belong to this category, and they are heavily inspired from reconstruction methods in X-ray crystallography. But there has been methods recently developed that belong to the way of data category. I have a list here. Model Angelo is probably the most powerful method for de novo model building. And it's considered state-of-the-art for model building. However, all those methods, if you use them, we've mentioned that earlier, if you use them as is, they will provide incomplete or sometimes slightly inaccurate model, and you need that manual refinement step. So we were wondering if we could use this diffusion-based prior to automatically refine incomplete atomic models. So I look a little bit into the details of that operator that transforms an atomic model into a density map to understand how the method works here. So the measurement, the density map here, can be expressed as a function of the atomic model, where gamma essentially places centrosymmetric densities around each atom, and that B operator stands for the application of the B factors, which you can think of as per atom motion blur in a very hand-wavy way. And now we suppose that there is noise on top of that noise-free structure, and we assume that noise to be Gaussian in this case, which gives us an expression for the negative log likelihood of a density map given an atomic model. And this is the log likelihood that we're going to compute the gradient of with respect to x. Now I'll just show a few results. We have in the first column the density map. Again, this one was simulated from a ground truth protein structure, and that's the conditioning information. The second conditioning information is that incomplete model that Model Angelo gives us from the density map. So you can see that parts of the structure are very well reconstructed, but some of parts are missing. So we want to fill in those gaps. And here I'm showing the output, one output of the method, and here a superimposition of 5 outputs. So it better shows where the method has high variance and where the variance is smaller. And if I look more quantitatively at the RMSD, so I didn't want to directly compare the RMSD with the ground truth structure between an incomplete and a complete model. So what I'm showing here is the RMSD versus completeness of the structure. Yes, sorry. Yeah.
Can I ask, where does the stochasticity come from? Like, how do you get multiple samples?
The denoising function has some randomness in it.
Okay, there's some draws from a distribution inside of there somewhere.
Yes.
Do I interpret these as members of as like appropriately weighted members of the posterior, or
or are they just like different guesses at the best math?
I wouldn't make the claim that this is a true posterior sampling method, because this is all based on essentially the plug and play method, which starts by framing the problem as a maximum a posteriori problem. So the variance that you have, there is no reason that this really reflects the posterior variance. Yeah. But so that plot shows you that if you look at a given completeness level, you have a lower RMSD, or for a given RMSD, you have slightly more complete atomic model. Now we also performed an ablation study just to understand what was the most important conditioning information here. So we removed some of the conditioning information one by one. We removed the incomplete model from Model Angelo. We removed the density map, the diffusion model sequence, and we ranked them here by order of importance. So what this plot shows is that the most important information is the incomplete model from Model Angelo. So this really shows that the method right now doesn't cope with de novo model building, but really with model refinements. Now, the second most important is the density map. That could be expected. And then the diffusion also helps you. And interestingly, the sequence doesn't help you that much. And this might be related to the capacity of the diffusion model we're working with. I'll say a few words about the last nonlinear problem we were looking at, the distances to structure. Yes, sure.
What does it mean to remove the diffusion that you're saying just take a single denoising?
We are, and it means we were just doing gradient descent on the likelihood. Yes. So the last linear problem we're looking at is distances to structure. We have this target structure. We compute the distance matrix between pairs of alpha carbons. And then our input is a sparse set from this distance matrix. And we're looking at the reconstructed structure as a function of the number of pairwise distances that we consider. So here is a plot with the RMSD as a function of this number. And we've also made this experiment of removing the prior, and you can really see that the RMSD decreases when you use the diffusion-based prior. As I was mentioning earlier, we also experimented with RF diffusion instead of chroma, at least with the two tasks, structure completion and distances to structure. We've done that on a few proteins from the Cas15 database because we knew that both those were not part of the training set of RF diffusion nor of chroma. The takeaway here is that, well, they both perform way better than when you don't use the prior, but it seems that chroma also outperforms RF diffusion in most of the cases, especially when the problem is well constrained. So when, for example, you look at the column 1/2 in the structure completion task, or 1/8 in the distances to structure task. So the takeaways are that we can combine a data-driven diffusion model with a physics-based likelihood, which has the benefit of leveraging the existence of large data sets of protein structures, but also circumventing the need for paired data. One way we showed that this was possible was by making use of variable splitting, and in this case, half-quadratic splitting. And we applied that to structure completion, model refinement, and its distances to structure problem. We validated the method on synthetic data, and now we're testing it on the real data, which is a work in progress. A few open questions I wanted to mention. So first, the question of validation, I think, is crucial here. How do you validate the structure now that you're using a prior that can be potentially biased? So to come back to this validation process in a protocol in cryo-EM, what people usually do is that they split the data set in 2 halves and give those 2 halves to the reconstruction method and see how the output differs, which is a way to quantify the variance of your estimates, but you cannot estimate the bias. And in this case, since we're using a prior that can be potentially biased, I think this can be an issue. There's also the question of how do you leverage other generative models like autoregressive models. ESM3, for example, is an autoregressive model, and what I've described today doesn't explain how you could use those autoregressive models. And taking a step back in this comparison between data-based and likelihood-based approaches, it's obvious that if you don't have access to paired data, the only thing that you can do is a likelihood-based approach. Now, if you have unlimited access to compute and to data, what people sometimes refer to as the bitter lesson of machine learning is that the fully supervised approach will probably win in the long run. But in practice, we never have access to infinite data and infinite compute. So I think the question of where is the break-even point between those two approaches is important, especially in helping us understand how much of the knowledge of the physics of the problem we should inject in the reconstruction method as people who design the reconstruction methods. And I'll quickly end with the second part, which is again more hypothetical and more about questions. So I think looking ahead, one next step for those generative models is to go into the dynamic domains. So we know that proteins are dynamic objects, and however, the current generative models are built to output static structures. So the question is, can we go beyond this paradigm and build generative models that would output ensembles of structures? And if we ask this question, we open a lot more questions. And I think the first one would be, how do you even define, or how do you even represent an ensemble of structures, that a discrete object, discrete set, and you also represent transition probabilities, or do you want to represent it as a continuous object with weighted latent space and a parameterized function that would map that to atomic models, or even to something more compressed, like I'm referring here to the tokens that are more and more used as compressed representation of high-dimensional objects.
I have an opinion.
Yes.
I don't know. I think the first one you showed is one that just directly translates to so much of biochemistry, and that's how you conceptualize states of ligands on off. I feel like that would be like immediately useful. That's my opinion.
Okay. Yeah, and I think the third one, yeah, is not like I don't think you should always. There is an explicit reason why we should go towards like tokens, which may sound like a fancy word, but I think the main reason why people use those tokenized representation is for compression reasons. So I think, yeah, also understanding whether those ensemble structures can be compressed in lower dimensional representations is quite important. But what if we had such, just connecting to the rest of the presentation, what if we had such a model? Well, we could broaden the scope of those map estimation problem and essentially transfer the solution space to the space of ensembles of structure. If we have a measurement process that preserves in some way the ensemble information, but this is the case, for example, for cryo-EM images. And now here, the prior would be directly a prior on ensembles of structure. And we could think of a method that would take a stack of images of cryo-EM images and a generative model over protein ensembles and output an ensemble of structure, not a single structure. Now, what's missing towards that, we said that we have to choose the right primitive, so the right mathematical object, I think, to represent those ensembles. We also have to choose the right model, which entails two things. I think first, the architecture. And when you think about the architecture of the model, I think this boils down to what are the invariants or equivariances that you know exist and that you want your model to have by construction. And also, what's the sampling algorithm that you want to use? Do you want to use something that's diffusion-based, that's autoregressive, or a mix of both, something completely different? And then, most importantly, I think choosing the right data for training. Where should the training data come from? Seems that if we're training more and more complex model, will be at some point limited in terms of data. So how much data do we need? And maybe more importantly, at which quality? And I just wanted to make a very loose parallel with the training of large language models, which I think capacity have been enabled by the fact that people were using low quality data to pre-train them and then high quality data to fine-tune them. I conclude briefly by saying that we witnessed in the past years successful development of diffusion models, and those can be combined with real-world measurements to solve inverse problems in different fields like computational imaging, but also structural biology. The project I've been talking about, ADP3D, applies that to atomic model refinements. And looking ahead, I think we could open a lot of doors by having generative models that reason about ensembles of structures. And with that, I'd like to thank all my collaborators. I would like to thank you for your attention, and I'm happy to take questions.
I have a question, like how does the maps resolution affect your ADP results?
Yeah, I think it's mostly because the completeness of the output of Model is gonna decrease.
I was wondering, so Chroma, RF diffusion are both backbone only diffusion models, or using RF
yes.
diffusion all atom?
The Chroma, the diffusion process of Chroma is only defined in the backbone space, but Chroma has this additional sampler to sample side chains, and that is an autoregressive model.
Okay, I see. Have you considered using Pardel or like an all atom model like that might be able to you know, it's doing the denoising all in atomic space.
I think especially for model refinement where the sidechain, you have to represent the sidechains. I think having a diffusion model that directly operates in all atom structures is crucial. And yes, you gave an example of such a model, but we haven't tried it yet. So yeah.
Another question is like, have you thought about like replacing your like map feed likelihood to be like single particle image likelihood?
Oh yeah, yes, that's something we want to look into. We're not sure what would be the real.
I'm just thinking like would the radius convergence of the loss function would affect the performance of the model of the framework. It's basically like you would imagine like the loss function from the single particle image would be like much more noisy.
Yes. So are you thinking that that would be a good thing or a bad thing?
That would be like a good test, but like much more challenging.
Yes, you're right. Yeah, I think you would have your gradient essentially would be much more noisy.
Yeah.
And you have to have a way to cope with that noise. Yeah.
I was wondering, when you're so Chroma also has the like conditioners framework. When looking at sort of differences between how strongly the outside like observation that you're imposing on the model affect the outputs, have you seen like how do those tend to differ? Because I mean, shape conditioner is a completely different framework, more akin to like a guided diffusion situation. But yeah.
So we compared ADP 3D to this posterior sampling or this conditioning framework of Chroma for the problems that could be resolved by the built-in conditioners of Chroma, and that's the case for this structure completion problem. And I mean the results of the posterior sampling method of Chroma are good, but if you look at the RMSD, we're reaching something slightly we're reaching like a lower RMSD, and I think this goes down. This is more a question of we're using this half quadratic splitting method, which might be better behaved, especially for problems where where your problem is well constrained, where you have enough observation for essentially the map estimate to be unique and the posterior distribution to be very unimodal. I think that's the case where our method performs better.
And so in that case, the Chroma conditioner framework, maybe the amount of information provided isn't enough to constrain to a unique sample.
Yes. Yeah, you lose like I think you pay some accuracy to have the benefit of having an uncertainty estimate. That's maybe one way to look at it. Yeah.
See that you are presenting only simulated data. You are trying with experimental one, but the fact that you are not presenting is because it behaves very differently from the simulated data, or
the reason actually is that we want to push the method towards being able to cope with heterogeneity. So yeah, this is really like something we're currently working on, but the idea we want to explore is, well, those heterogeneous reconstruction methods, they don't give you a single density map, they give you an ensemble of density map. If you think of CryoDragon for example. So can you use this ensemble of density map to have an ensemble of atomic models? And yeah, I think this would.
But if you try with a single map, it behaves the same as it with simulated data.
Well, it depends on so if you have a lot of if you have residual compositional heterogeneity, so complexes that we bind and unbind, this is not handled by the method very, very well. So Yeah, I mean, most of our experiments with experimental data are focused on this heterogeneous problem, and and setup, and we have like preliminary results on that, but not on the homogeneous case, which sounds less interesting to us.
Yeah, but still, Model Angelo couldn't fit the whole map, so
Yeah.
would be useful.
Yes, but I think if we look at like the places that have been inpainted by the method right now, there is still a significant difference, and I think there is still a need for someone to look at the model and manually fix it. So I think from a practical point of view, the method would be more useful if it could cope with heterogeneous. Yeah.
So you're thinking to like send a bunch of maps from a prior dragon latent space.
Yeah. Yeah.
I mean, would there be a way that you could like jointly discover the vacant space as part of the single optimization?
Yeah, I think that would be the next,
that's the next
step, and work directly
what's-
from images.
What's your institution? What's the like? I don't know. What's the ETA for that? Like 10 years? Am I being too pessimistic?
Yeah, I would say hopefully less. But I think we would need also to solve that problem of how do you use images instead of density maps in the first place.
It could be some like code optimization.
And you'd have to add the unknown pose problem on top of that.
Yeah.
That's
Do you have an opinion on if the priors you're using, like RF diffusion and chroma and stuff, which are sort of, like trained on PDB, et cetera, like, do they have the capacity to generate a metastable state that might be present?
I think that's
And it's like sort of the interesting
Yeah.
fringe that you want to represent.
yes. Unfortunately, I think since they were all trained on one structure that was the most stable, I think they wouldn't cope very well with that.
This wouldn't work with RNA structures, no, or DNA.
If you have a diffusion model that works with DNA structures, then yeah, potentially.
Okay, thank you, Axel.